Hi, I'm Giosuè Saibene. I'm a PhD student of Università di Studi dell'Insubria in Italy. And in my talk, I will explain the ENUBET idea, the detector that we build, and the beam test characterization that we have done. So you know that there are many problems and many open questions about neutrinos here and also in current and future neutrino experiment. For example, the measurement of the delta CP parameter in the Kabib-Kobayashi-Masawa matrix, or also which is the correct mass ordering, or also a better determination in the oscillation parameters. Some uncertainties are, for example, the neutrino flux, the interaction cross-section, and the detector efficiency. Well, okay. Our process of interest is the charge current interaction with nuclei in the GeV range. So our idea is ENUBET, so enhanced neutrino beams from count tagging. So we want to have a measurement of neutrino indirectly. So we want to measure the, if I can, no, okay. Well, we have to detect the leptons in, okay. The, like old style school. The lepton generated at a large angle. So if we detect one lepton, we will have one neutrino. We want to measure the neutrino flux with a high precision in order to have to reduce the precision of from 10 to 1% of the neutrino cross section. So our detector is a calorimeter. We want to measure the energy of the leptons. We build the two versions, one with 400 channels and one with 1200 channels. And they are composed of alternating layers of iron and plus these utility lights. In order, we have two tiles without the iron in between. And I will say in a moment why we have done this choice. So our idea is to monitor and tag the lepton signal instead of all the sources of the ground. We have schematized our detector, which is segmented in all the three directions. So our signal is one or two heated layers. Instead, for example, a muon has a straight trajectory, and also the energy deposition in all detectors is always the same. Instead, for example, a charged pions has a much higher energy deposition, and also a number of little tiles or channels are much more. The pi zero, or the two gammas, which are neutral particles, have the same shape of our signal, our positrons. So with the two layers without the iron in between, we can discriminate the charged particle with the neutral one. So we can use these two with this thing. So, okay, we build our detector. We bought it at CERN and at the T9 beam line, and we have tested it. First of all, we have to equalize all of our channel, because every CPM have a different response of the same amount of light. So how we do this? We take the efficiency map. We take a fiducial area. We select the MIPS in this area. We compute in the center of gravity, and then we fit with a Landau shape. And every channel has his peak and his baseline value. So we can equalize all of the channels. Then we can sum the response of all of our detector. So we can measure the energy deposition histogram. We can fit with a Gaussian function, and we can compute the linearity, the calibration, the linearity, and the energy resolution. These two values are compatible with a smaller prototype, and also compatible through the 3 years of data taking. Another analysis is the crosstalk, because as you can see, we have wavelength shifting fibers that passes through the other plastic scintillator. So some light could be lost and could affect. We have studied the crosstalk, and we have a less than 5% for all of the channels. So we are happy with this readout scheme. The most important part is this particle identification test, because we want to select leptons to all of the other sources of the ground. So we have computed two parameters. So the number of tiles over a set threshold, so that are heated, and the deposit energy in our demonstrator, in our detector. We have computed the B-plot of this parameter, and we can see three different spots, electrons, muons, and hadrons, and making a threshold. Over that, there are all electrons, and above, there are muons and hadrons. And these are the predicted values. The true values are the ones of the Cherenkov detector present in the beamline. So we have computed the accuracy, so the fraction of event correctly classified, and the precision, so the fraction of event correctly predicted, and we have some good values for our first test of particle discrimination. Another type of particle discrimination is with, for example, two different beams impinging in on a horizontal position of our demonstrator. And we can see that we can also select the electrons energy deposition instead of, for example, pions or muons in a hadron beam. Or even if we have an electron beam, we can see that there is a component of muons and pions with this analysis. The last thing that I wanted to show you is that we have also tilted our demonstrator respect to the beam direction with an 100 and 200 tilting angle. And we can see that we can study the energy deposition through the Z layer, so in the beam direction. And we can see that, for example, with 100 millirad, all of the total is the green one. And we can see that the red one, which is only the first rider layer, is all here. Instead, for example, with 200 millirad, we have the shower development, which is in the first two radial layer, and also in different Z position, there is the peak. So we can also discriminate maybe with this other technique of our signal to our background. So in conclusion, we have performed a 3-year beam test data, and we have a basic performance of our demonstrator. The linearity and energy resolution are compatible with previous prototypes, and also through the 3 years are consistent. We are happy with our outward readout scheme of the crosstalk, and also we are in a good way of good preliminary result with particle identification, and also with energy deposition with different beams, or also with different tilting angle. So thank you. And
are there any questions?
Nice talk. I had a question about, so when you say the beam and the beam, so this was one of the last slides.
Yeah.
So when you say beam, what exactly do you mean here? The kaons coming in, or?
No, here we use a hadron or a electron beam,
Yeah.
and which is in this way, and we have tilted our demonstrator in order to simulate a different impinging, not horizontal, but maybe with different.
So the Z layers you talk about are,
yeah,
are
the
they
Z
horizontal?
is the horizontal
Okay.
position. Yeah.
Okay. Thanks.
Thank you for your talk. Since in the process you're studying a pi zero is also produced in the final state, and you showed in a slide that you might be able to identify also pi zero by looking at the absence of a track. Would you maybe be able also to exploit the detection of pi zero to operate the detector in the coincidence between a pi zero and a kaon to improve, for example, particle identification?
Yeah, I don't know, because yeah, pi zero decays immediately into gammas. So maybe this is the source is the gammas, which is similar to electrons. So maybe the scheme of without the two layer without the iron, we can discriminate them instead of maybe simulating the shower or something else. No, I don't know if I answered your question.
Yeah. Thank you.
Okay.
Are there any other questions? If not, let us thank Giosuè again.